Welcome back. So in this chapter, we're going to start with a couple of bonding. We need to know how to draw the structure of a molecule, because in organic chemistry, main thing that you have to focus on it, what's the geometry and what's going to happen with shape of molecules while we are moving from reactant to products. Okay, let's start with this. What's the organic chemistry? Organic chemistry is a science that is trying to study molecules that they are mainly carbon-based. Why do I need to know organic chemistry, or what's the difference between organic chemistry and inorganic chemistry? The main difference between organic and inorganic, in organic, you will have a molecule that's made of non-metals, okay? Non-metals. Now, inorganic, there will be one metal there, okay? So if we have a metal, we're going to call it inorganic. And now what will happen if I add metal to an organic, organic molecule? In that case, we're going to call it organometallic compound. Okay. Why do I need to know organic chemistry? Because our life is based on technically organic molecules. You are an organic lab, so we need to know exactly what's going on with our body, and best way to understand it is to know the organic science, actually. Okay. Next thing is, why do I need to know a couple of formulas, more than one formula for one molecule? Why do I need to know how to name it, or how to draw the structure? So based on the way the way atoms get connected to each other, you might get different physical and chemical properties. So one single formula is not going to represent everything about that molecule. Okay, we're going to start with constitutional and isomers. And okay, what's the isomer? Isomer, if you have two formulas that the only difference between them is connectivity, in that case, we're going to call them isomer. Now, the constitutional isomers, okay, the constitutional isomers are the isomers that's only difference between them is just the way they are connected to each other. Later, I will introduce a bunch of like a different isomers that's like the connectivity is the same, it still is the same, but we call them isomer. Why? Because the way we arrange them in a space is a bit different. Okay, let's do one example here. For example, we have a molecule that the formula for it is this. We have C, okay, say C6, and H, we have 6 of them, and oxygen 1. Okay, how can I actually draw molecule based on this formula? I can say, you know what, let's put a carbon here, okay, attached to one oxygen, attached to another carbon, and each carbon, we're going to give it 3 hydrogens, okay, because we are going to follow octet rules. That's one molecule, and the name for this one is ether. Okay, why ether? Because of this bridge. Okay, so the functional group here, we call it ether. Now, if you take the first one, carbon attached to 3 hydrogens, then attach this one to the second carbon with 2 hydrogens, and put oxygen after the second carbon. Now attach it to hydrogen. This is going to be alcohol, and the name for it will be ethanol. And this is your functional group. You will learn it later. Okay, so I got 2 molecules that have exactly the same formula. The only difference between them, the way I arranged it, their connectivity is different. Okay, oxygen used to be bridge. Now oxygen, I put it almost like as a terminal atom. Okay, and if you can draw two molecules or 2 formulas, 2 structures, that the only difference between them is the connectivity, we say you are dealing with isomers. Okay, and these 2 isomers are constitutional. Okay. Okay. What will happen during a chemical reaction? In a chemical reaction, you're not going to change, the atoms. The atoms will be the same. Okay. And the atoms, and each atom is made of proton, neutron, and electron. So we will never ever touch technically the protons or neutrons, because they are inside the nucleus. Okay. So the thing that is changing most of the time will be number of electrons. You are going to exchange electron with like your neighbor. Now, if the one atom is giving or accepting electron from neighbor, in that case we say now we have a chemical reaction. Okay. So I want to actually talk about structure of atom, and then show you something that we used to call it electron configuration. So as a reminder, each element is going to be made of a nucleus, and so inside the nucleus we have, this is our nucleus. Inside the nucleus we have protons. Okay. Proton, it has a positive charge, and the charge is a +1. Okay, and what else outside? Okay, outside of the nucleus. So the one that's I'm going to highlight, this is the nucleus, and outside the yellow one, we're going to have electron. And this one, I'm going to call it level of energy or shell. Okay, level of energy or shell. Okay, and you will find the electrons inside the shell. Okay, first shell or level of energy, it can accommodate 2 electrons, and while the second one is going to have 2 + 6, it will be 8. Okay, so again, let's draw. Okay, draw a nucleus. So we have a tiny area that we call it nucleus. Next, we're going to have first orbit. That's going to be the second orbit. Then you will have, for example, the third orbit. Okay, so I'm gonna call the orbits. I'm gonna show them by n. Okay, so go. Okay. N. Okay, we're gonna call it level of energy or shell. Okay, you can call it also orbit. Okay, you can call it orbit. Electrons will be inside of the orbits, hanging around the nucleus. And inside the nucleus, you will have protons. Here we have protons and neutrons. Okay, the first layer it can accommodate, I'm going to call it N1, and this is going to be N2, and that one is N3. The first layer it can accommodate 2 electrons. The second layer, 2 plus 6, it will be 8. And the third layer, it will be 2 plus 6 plus 10. And that can accommodate 18 electrons. So 18 here, 8 there, 2 electrons. Okay, first layer. Okay. So first shell or layer, and we're going to call it N1. It has one orbital, okay, place that you can find electron in it, and that orbital, the name for it is S orbital. S orbital is made of one box. That means it can accommodate 2 electrons. One is pointing up, and the second one will be pointing down. Okay, so we say we have one orbital belonging to the first layer, and the name for it is S, and it can accommodate 2 electrons. The second layer, or second shell, go N2, it can have 2s, that it can accommodate 2 electrons, plus 2p orbital, and that orbital is capable of accommodating 6 electrons. Okay, S orbital is made of one box, while the p orbital will be made of 3 boxes. Sorry. So we're going to put 2 electrons inside the first orbital, and then okay, 1 electron in each p orbital, and the second one will be pointing down. Okay, so first orbital, call it 2s with 2 electrons, and this is 2p orbital with 6 electrons. In organic chemistry, mainly you will be dealing with s and p orbitals. Okay, and why do I have 10 electrons here? According to I get those 10 electrons because when you start the third layer, you're going to have 3s orbital plus 3p and 3d orbital. The 3s, it can accommodate 2 electrons, 3p 6, and 3d 10 electrons, and that totally will be equal to 18 electrons. So now let's go back to the slides. Okay, so we said in organic chemistry, we will be focusing on non-metals, mainly carbon, nitrogen, phosphorus, or oxygen. Okay, and the electrons are the one that we are going to follow. Okay, electron, it has a negative 1 charge and is exactly equal to the charge of 1 electron. I want to remind you what's the meaning of valence or core electrons. Okay. The way we distribute electrons inside orbital of each element, we call it electron configuration. Hydrogen orbital, it has 1 orbital, and the s orbital. Okay, well, helium, it has 2 electrons. So you say, I'm gonna put 2 electrons inside of the 1s orbital. So first orbital, it will be 1s1. That's going to be 1s2. Now, if you move to lithium, you have 3 electrons. So what do we do with them? 2 of them we put them inside 1s orbital. So we go 1s2. Still, I have three more. I have one more electron, and I'm going to put it inside 1s orbital. And you keep doing this one until you accommodate all the electrons. Now, what will happen if you have 5 or more electrons? Okay, for example, when we are dealing with boron has 5 electrons. So you go 1s2, 2s2, and now 2p1. Okay, so the way we distribute the electrons inside the orbital, we call it electron configuration. Okay, let me remind you how to get actually electron configuration of any element. Okay, go with this. Okay, we have s orbital. It can accommodate 2 electrons, and p orbital. It can accommodate 6 electrons, and d orbital. It can accommodate 10 electrons because it's made of 5 orbitals. They go up, 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 down, down, down. Well, let's go with different color. Down, down, down. Then here we go up, 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 up. Now I will pair them. Okay. Use this. Okay. So we have 1s with 2 electrons. That's belong to the first layer. Now 2s with 2 electrons, 2p, 6 electron, 3s, 2 electrons, 3p, 6. Then I go 4s, 2, and here 3d, okay, 3d, 10. And after 3d, again, we're going to have 4p. Okay, 4p can accommodate 6 electrons. That should be more than enough, honestly, to accommodate in like most of the non-metals. Okay. Again, how did I get those orbitals? Go with this, and 1, and 2, and 3, and 4. Okay, first layer, it has 1 orbital, and the name for it is 1s. Second layer, it has 2 orbital. First one, 2s. Now you're going to get a new orbital, and that's going to be 2p. Third layer, it has 3 orbital, 3s, 3p, and the new orbital is going to be 3d. Okay, the fourth layer, it has 4 orbital. You go 4s, 4p, 4d, and the new orbital is going to be 4f orbital. Okay. Now, if you don't remember anything about electron configuration, or you don't know really how to kind of like put the orbitals after each other, start with this. Okay. Say they gave you this. They said we have an element like a chlorine with 17 electrons, and we want to know what's the electron configuration for it. Okay. So remember, you have 17 electrons. S, it can accommodate 2 electrons, P 6, and D 10 electrons. So remember this one for yourself. Okay. Pass a vector from the first orbital. Okay. So one vector from the first orbital is passing 1s. So I'm going to say, okay, first orbital is 1s, and it can accommodate 2 electrons. Okay. Next, the second vector, it will go parallel to the first one, and it's passing only 2s. So I'm going to say next orbital, it will be the 2s with 2 electrons. The third orbital, the third vector, okay, so the third one, okay, let's go with red, is passing 2p first, and then 3s. So I'm going to say first 2p with, okay, 2p with 6 electrons, and then I get 3s with 2 electrons. So until now, I managed to accommodate, okay, 2, 2, 6, and 2, that's 12 electrons. Remember, chlorine is supposed to have 17 electrons. So I'm missing some of them. I'm missing 5 of them. Where should I put the rest? The rest, okay, you draw another vector parallel to the third one, and that is passing 3p, okay, passing the 3p first. So I go 3p, okay, until here, we have 10 electrons, 2 plus 12, 10, it will be 12. So in p orbital, I'm going to have 5 electrons, okay, 5 electrons, and that's going to be electron configuration of chlorine. Okay, so I'm going to erase this area for a second. Okay, let me erase this. Okay, so we said the first layer, N1, it has 2 electrons. The second layer, N2, we have 2s, 2 plus 2p, 6. That means it's 8 electrons. But the third layer, N equal 3, we have 3s with 2 electrons plus 3p with 5 electrons. Okay, I want you to highlight the highest orbit, okay, or layer. Okay, the highest orbit or layer, okay, the highest n is equal to 3, and we're going to call this one period. This element belongs to the third period. Okay, next, electrons of the last layer, we're going to call them valence electrons. Okay, so electrons of the last shell or layer, we call them valence electrons. Okay, So now that you figured the highest n is equal to 3, look to n equal 3 and ask yourself, how many electrons there? So we're going to say valence electron equal to group is going to be 2 inside the 3s orbital. Okay, I'm going to highlight them. So I have 2 electrons here plus 5, 2 plus 5. This element belongs to group 7. So chlorine belongs to the third period in group 7. Okay. So now that we figured the valence electrons, let's talk about rest of the electrons. What should I call them? Okay. I'm going to just minimize. Sorry, I'm going to shrink the size of those. Need more space. Okay. Rest of the electrons, we call them core electrons or inner electrons. You are not going to be dealing with core electrons. In order to reach the core or inner electrons, you really need to have X-ray or gamma, energy to touch technically those electrons. So in organic chemistry, we will not be dealing with core or inner electrons, only and only valence electrons. Okay. Another way to write the electron configuration. Okay. So for chlorine, we said 1s2, 2s2, 2p6, and then we said 3s2, 3p5. Okay. If you compare electron configuration of chlorine with neon, it has 10 electrons. Okay. Neon is 1s2, 2s2, 2p6. So you can write electron configuration of chlorine as neon, the previous noble gas. Okay, the previous noble gas, neon, that represents 10 electrons. And then write rest of the electrons and orbitals. 3s2 and then 3p5. Always you need to keep the valence electrons out. Okay, so I'm going to stop here. Okay, and I will be talking about electron configuration and also electronegativity in the next video. Thank you very much.